let us see the conformational analysis. The different spatial arrangement of atoms that results from rotation of groups about carbon-carbon single bond is called conformational isomers or rotational isomers. The energy difference between two extreme conformations is very small. Thus, rapid interconversion takes place at room temperature between different conformers. It is not possible to separate one conformer from other. Low energy, we can only say that low energy conformer is more populated than high energy conformer at room temperature. Let us look at conformations of ethane. Conformations of ethane CS3 results from rotation of back CS3 group with respect to the front CS3 group. We can imagine front CS3 group as fixed position and back CS3 is rotating with respect to front CS3. The conformations are always shown better with the Newman projection formula. Let us see the next slide. Let us see the conformations of ethane. This formula represents the eclipsed conformation. This is the Newman projection formula. The bonds drawn from the center of the circle represent the front carbon atom. The bonds drawn from the circumference of the circle represents the back carbon atom. This formula represents the eclipsed conformation since the dihedral angle between the hydrogen atom is 0 here, because this hydrogen atom is in eclipsing. They are on same line, eclipsing with the back carbon hydrogen on the back carbon atom. This is high energy conformation because there will be maximum bond hydrogen carbon hydrogen bond repulsion in this conformer, and this is the high energy conformation represented by and dihedral angle 0. We have high energy. There is an energy difference of 12 kilojoules per mole between eclipsed and staggered conformations. We will discuss that one later. This is the dihedral angle 0. If you rotate the back carbon atom 60 degree in the clockwise direction while keeping the front carbon atom in same position, we get this isomer. We rotate back carbon atom 60 degree. So this hydrogen comes here. So this is the representation, and dihedral angle becomes 60 degree. Dihedral angle is actually this is a projection formula, and in projection formula the dihedral angle in a plane becomes 60 degree. 60 degree dihedral angle. This is the another extreme conformation called staggered conformation. Eclipsed and staggered conformations are two extreme conformations. In between the two extreme conformations, there are infinite number of conformations possible depending upon the dihedral angle. Dihedral angle can vary from 0 degree to 60 degree. So we have infinite number of conformations between these two angles. So this is another conformation. So this in this conformation, hydrogen is not eclipsing. It is in staggered arrangement with the back hydrogen. So the repulsion between carbon hydrogen bond, this carbon hydrogen bond and this carbon hydrogen bond is less because the distance between the bonds are maximum. So this is the most stable conformation in ethane. So we can say that if you have a mixture of, if you have ethane sample, we can only say that staggered conformation is more populated than the eclipsed conformation, because the energy is less for staggered conformation, whereas energy of eclipsed conformation is about 12 kilojoules per mole higher than the staggered conformation. This is the dihedral angle 0. When dihedral angle becomes 60 degree, we get minimum energy conformation or staggered conformation. So this is a Newman projection formula, and dihedral, based on dihedral angle we can draw this potential energy diagram. When dihedral angle becomes 60 degree, we have minimum energy conformation. Again, if you rotate the bicarbon atom clockwise another 60 degree, we again get an eclipsed conformation. So we get this point, again we get eclipsed conformation. If you rotate so 120 degree dihedral angle, we have again eclipsing. Again, if you rotate another 60 degree, dihedral angle become 180 degree. 180 degrees, so we again get staggered conformation. Staggered conformation. If you rotate another 60 degree again, we again get eclipsed conformation. 250 degree we have eclipsed conformation. If you rotate again another 60 degree, we get again the staggered conformation at 300 degree dihedral angle. If you rotate again 360 degree, you get back the original eclipsed conformation given by 360 degree dihedral angle. We have eclipsing again. So this is the conformations of ethane. Let us see the conformations of butane. Conformations of butane: CS3, CH2, CH2, CH3. About C2-C3 bond is important. This is the first carbon atom, second carbon atom, third carbon atom, and fourth carbon atom. About the 2-3 bond is important. Here the structure, let us coming to the graph. The structure D represents the Newman projection formula of this butane. Here this is the first carbon atom and this is second carbon atom on this front center of the circle. Red CH3 is the first carbon atom, the second carbon atom. Back carbon atom, this round circle represents the back carbon atom in Newman projection formula. Is the third carbon atom, and the blue CH3 group is the fourth carbon atom. In the structure D, the bulky CH3 groups are coming with the dihedral angle 0. This structure is the most unstable conformation because highest energy conformation, because the energy difference between the most stable conformation A and the structure D is about 19 kilojoules per mole. This conformation is called fully eclipsed conformation because CH3 bulky CH3 groups are coming in the same direction with the dihedral angle 0. Let us look at if you rotate the red CH3 group, the front CH3 group through 60 degree in anti-clockwise direction, this CH3 comes here. So we get the structure D. Here the bulky CH3 groups are at a dihedral angle of 60 degree. This conformation is called Gaussian conformation. This is not the stablest conformation, and here the dihedral angle is 60 degree. The energy difference between the most stable conformation A and this conformation is about 3.8 kilojoules per mole. This conformation is called Gaussian conformation. Then look at next conformation. If you rotate again the red CH3 through another 60 degree, this CH3 group come in eclipse with the hydrogen atom here in the back carbon atom. So this conformation is obtained, and in this conformation the eclipsing is there, but not as eclipsed as the structure D. Here the CH3 group is eclipsing only with the hydrogen atom. This conformation is called eclipsed conformation, whereas the structure D is called fully eclipsed conformation. Let us see the energy difference between the most stable conformation A and this conformation is about 16 kilojoules per mole. If you rotate another 60 degree, you get structure A, another 60 degree in anti-clockwise direction. Structure A is obtained. Here the red CH3 comes here, and the red CH3 comes in opposite to that of the CH3 group on the back carbon atom, and the repulsion between the CH3 group, bulky CH3 group, is minimum here. This conformation is called anti-conformation because the CH3 group are far apart, and this conformation is anti-conformation. It is the stablest conformation in butane. Let us look at clockwise rotation of the red CH3 group. If you rotate clockwise another 60 degree in the clockwise direction, you get this red CH3 comes here, and you get this conformation. This conformation is same as that of this structure B. This structure B is obtained. This conformation is called Gaussian conformation. The energy difference is same, is about 3.8 kilojoules per mole. And if you rotate another 60 degree, the structure C is obtained, the same as that of this one. This conformation is called eclipsed conformation. The energy difference is about 16 kilojoules per mole. Here the CH3 group is in eclipsing with the hydrogen atom. If you rotate the front carbon atom red CH3 through another 60 degree, you get structure A, similar to that of structure A. The minimum energy conformation is obtained. Here this conformation is called anti-conformation. Let us see the conformations of cyclohexane. In cyclohexane, if we assume planar geometry, as in the case of benzene, carbon-carbon-carbon bond angle, CCC bond angle, become 120 degree. There is large bond angle strain due to high deviation from tetrahedral bond angle of 109.5 degree. Therefore, the molecule will not assume planar geometry. They assume a spatial geometry. Chair and boat forms are two conformations of cyclohexane in which tetrahedral bond angle of 109 degree, 109.5 degree is maintained. In both and chair forms, there is no bond angle strain because it maintains a tetrahedral bond angle. Let us look at the chair conformation. In chair conformation, all carbon-hydrogen bonds, there are 12 carbon-hydrogen bonds there in cyclohexane, all carbon-hydrogen bonds are staggered. There are two types of carbon-hydrogen bond in cyclohexane. One is axial cyclohexane bond, another one is equatorial. The vertical bonds are called axial bonds, the inclined bonds are called equatorial bonds. There are two types of bonds in this is the chair form. In chair form, all carbon-hydrogen bonds are staggered. If you look at 1, 2, this is the first carbon atom. We number like this 1, 2, 3, 4, 5, 6, 7, 5, 6. And if you number, this is the first carbon atom, it's the second carbon atom, third carbon atom. So 1, 2, if you look at 1, 2 bond, this hydrogen atom coming with staggered with respect to this hydrogen atom. This bond is staggered, and this bond is also 2, 3 bond is also staggered. 3, 4 bond is also staggered. If you look at this hydrogen atom and this hydrogen atom is staggered, and for this bond is also staggered. 4, 5 bond is also staggered, and you can see this hydrogen atom and this hydrogen atom, they are staggered conformation. And again, this is the 5th carbon atom and the 6th carbon atom also coming in staggered conformation. So all carbon bonds are staggered conformation. So this is the most stable conformation in cyclohexane. The chair form is the most stable one, and this bond is equatorial bond and this is axial bond. The presence of we can convert the axial bonds into equatorial bonds by process called flipping. And let us look at this figure. This is HA, hydrogen atom. HA is on axial line, whereas HB is coming in equatorial line. There can be carbon-carbon bond rotation inside the ring, and due to the carbon-carbon bond rotation, this CH3 comes down, this CH2 group comes down, and this fourth CH2 group come up, and we get this structure. And this process is called flipping. At room temperature, it undergo rapid flipping, and axial bond become, this axial HA bond become equatorial bond, and the equatorial bond become axial, HB become axial, and this process is called flipping. So if you take, this is evident from NMR spectroscopy. If you take NMR spectrum at room temperature, we cannot distinguish between axial and equatorial hydrogen atoms. If we take NMR spectrum at minus 60 degrees centigrade, this flipping rate becomes slow and is somewhat arrested at minus 60 degrees centigrade, and we can distinguish the axial hydrogen atom with equatorial hydrogen atom because two chemical shifts are obtained for HA and HB. Let us discuss bond form. In chair form, we have seen that all carbon-hydrogen bonds are staggered, whereas in bond form, there are two eclipsings, C2, C3 and C5, C6 bonds are eclipsed state. Thus, bond form is less stable from chair form by 28 kilojoules per mole due to eclipsing of C2, C3 and C5, C6 bonds. Let us look at first carbon atom and second carbon atom. This hydrogen atom and this hydrogen atom are staggered conformation. So 1,2 bond is staggered, whereas if you look at 2,3 bond, this hydrogen atom comes in eclipsing with this hydrogen atom. This hydrogen atom is also in eclipsing with this one. So there is eclipsing between 2,3 bond, and whereas 3,4 bond is staggered, we can see that this hydrogen atom is in staggered conformation with respect to these two hydrogen atoms. Dihedral angle 60 degree here. And if you look at this bond, 4,5 bond, this is also staggered. Whereas again, you look at the 5,6 bond, 5,6 bond is eclipsed. So 2,3 and 5,6 bonds are eclipsed. Thus, this conformation is less stable than chair conformation by an energy difference of 28 kilojoules per mole. Therefore, chair form is mostly stabilized, whereas bond form is less stabilized. But in certain molecules, bond form becomes stable. For example, cis-1,4 dihydroxycyclohexane. These two bonds are called flat pole bonds. Suppose two OH groups are coming at the flat pole positions. So in cis-1,4 dihydroxycyclohexane, this will come like this OH groups, and there will be hydrogen bonding. And this due to hydrogen bonding, the bond form may stabilize here. Similarly, we look at the camphor. In camphor, this is the bond form. It's a cyclohexane ring, this cyclohexane ring, and here these two bonds are flat pole bonds. When flat pole bonds are joined by a carbon atom at this apex, there are two CSO group there, and this carbon atom, and this type of bridgehead compounds, the bond form may stabilize. Let us look at conformations of monomethyl substituted cyclohexane. This is monomethyl substituted cyclohexane. Methyl group can be placed at axial position or equatorial position. Here in this molecule, methyl group is placed at axial position, whereas if you do flipping means this CH2 group comes down and this CH2 group come up due to carbon-carbon single bond rotation inside the ring. And the flipping process takes place, CH3 group in axial position comes to equatorial position as shown here. So let us evaluate which conformer is more stable, whether the axial methyl or equatorial methyl. Let us look at the axial methyl bond rapidly changes to equatorial bond by carbon-carbon bond rotation called flipping. Thus, axial methyl group cannot be separated from equatorial methyl cyclohexane. Axial methyl group has two Gaussian interactions. Let us look at Gaussian interactions as we have seen in butane. Butane about 2,3 bond we have seen there in the previous slide. There is Gaussian interaction, the CH3 group and the CH2 group in axial methyl cyclohexane. If you look at 1,2 bond of this is the first carbon atom, this is the second carbon atom. The second carbon atom is drawn as front carbon atom in Newman projection formula. This is a 1,2 bond, and this is second carbon atom, back carbon atom, the first carbon atom is drawn on the circle. If you look at the front carbon atom, this the third CH2 group is drawn here, CH2 group, and there is an equatorial hydrogen atom here that is drawn here, and there is an axial hydrogen atom here that is also drawn here. This is the front carbon atom. If you look at the back carbon atom is the first carbon atom, and we have a CH3 group in the here a CH2 group is drawn. Then we have a CH2 group of the 6th carbon atom that is drawn here, and there is a equatorial hydrogen coming down here, and that is drawn here. This is the back carbon atom drawn on the circle and front carbon atom. Here you can see that there is a Gauche interaction. A Gauche interaction means when two CH3 groups are coming like this, there is a Gauche form. Gauche form is not highly stable. It is an intermediate energy state, and there is a Gauche interaction in when axial methyl comes, and this destabilizes the system. And there is a Gauche interaction when axial methyl groups are coming like this between 1,2 bond. Similarly, we can when you look at through 1,6 bond, here also there is a Gauche interaction between the axial methyl group and this CH2 group. So as not showing that. Therefore, whenever there is a CH3 group in axial position, there will be two Gauche interactions. With the Gauche interactions are due to this CH3 group and this CH2 group of the third carbon atom about through 1,2 bond, and another Gauche interaction of the CH3 group with respect to 1,6 bond between the fifth CH2 group that is not drawn here. So there are two Gauche interaction comes when an axial methyl group is there in cyclohexane. When you look at equatorial conformer, axial group methyl group is transformed into equatorial one by flipping process, flipping or carbon-carbon bond rotation process. Here, when you draw the Newman projection formula, this is the front carbon, the first carbon atom, front carbon atom. This is the sixth. We are evaluating the Newman projection formula about 1,6 bond, and this first carbon atom, this CH3 group is drawn here, and second CH2 group is drawn here. This is a CH2 group, and there is a axial hydrogen atom that is drawn here about 1,6 bond. And we look at the sixth carbon atom. There is an axial hydrogen atom here, the back carbon atom, and there is an equatorial hydrogen atom here, the back carbon atom like this, and there is a CH2 group on the fifth carbon atom that is coming down like this, that is drawn like this. So these are the groups like this. Here we can see that there is no such a Gauche interaction because CH2 group is far apart from the CH3 group, whereas here CH2 group and CH3 group is dihedral angle 60 degree. Here dihedral angle is far apart. Dihedral angle is very high. Here dihedral angle is 190. Here dihedral angle is there is no here 190 degree dihedral angle because from the front carbon atom and the back carbon atom. So there is no Gauche interaction when axial methyl group is equatorial methyl group is substituted in the cyclohexane. There is no Gauche interaction in this molecule, in this structure, whereas here there are two Gauche interactions between in 1,2 bond and 1,6 bond. Thus, we can say that equatorial methyl is more populated, more stable and more populated than axial methyl conformer in an equilibrium mixture of two conformers. Next, we look at the conformations of dimethyl substituted cyclohexane. When there are two methyl groups substituted to cyclohexane, there are different possible isomers, position isomers. We can substitute at 1,1 position. This is the 1,1 dimethyl cyclohexane, and we can have 1,2 dimethyl cyclohexane and 1,3 dimethyl and 1,4. First, we look at 1,1 dimethyl cyclohexane. When there are two methyl groups are substituted at axial position and equatorial position, there is only one way. One methyl group is at axial position, other methyl group at equatorial position. Flipping, during flipping, the axial methyl group is converted to equatorial methyl and equatorial methyl is converted to axial methyl, that we have seen in the earlier slide. Therefore, on flipping, axial bonds are converted to equatorial bond and vice versa. Thus only one conformer exists in this one, because axial there is one axial methyl and one equatorial methyl is there. Only one conformer exists in this one. So we need not analyze any stability difference. Let us see 1,2-dimethyl cyclohexane. 1,2-dimethyl cyclohexane is a position isomer, one of the position isomer of dimethyl cyclohexane. 1,2-dimethyl. Here the methyl groups are attached at position 1 and position 2. There can be two geometrical isomers, cis and trans. Cis isomer never interconvert into trans isomer by flipping. Let us look at this is a cis isomer where CS3 groups are on same side, and this is the trans isomer. Here CS3 group is upward and CS3 group is downward. They are opposite. It is called a trans 1,2-dimethyl cyclohexane. This is cis 1,2-dimethyl cyclohexane. This is a Fischer projection formula drawn only in eclipsed conformation. Actually the molecule exists in staggered conformation. So for that you have to draw the staggered conformation. For that we have to go for the chair form. Chair form is staggered conformation, where the first carbon atom is here. First carbon atom, the methyl group is in axial position, and the second methyl group is in equatorial position. And by flipping we get the axial methyl group is converted to equatorial methyl group, and the equatorial methyl group is converted to second position is converted to axial methyl group. So these two forms are 1A. This can be represented as 1A, 2E. One first position we have axial methyl, and we have second carbon atom we have equatorial methyl. Similarly here 1E, first position the methyl group is equatorial, and second carbon atom we have axial methyl group. When you look at when you analyze the Gaussian interactions, as we have seen in the earlier slide, whenever there is an axial methyl group, there is two Gaussian interaction. One with respect to 1,2 bond, we have Gaussian interaction with the third CH2 group and this methyl group, and there is a Gaussian interaction. And also we have Gaussian interaction about 1,6 bond between the methyl group and the CH2 group. So there are two Gaussian interaction here in 1A, 2E, and we have, when you come here also 1E, 2E also we have. And here also we have to, whenever there is an axial group, methyl group, there are two Gaussian interactions. So 1A, 2E and 1E, 2A are equally stable. So I can either exist this form or this form, they are equally stable. Let us evaluate the trans isomer. Trans isomer can be represented in Fischer-Tropsch formula like this, and we have two conformations possible. Conformation. One is this is a chair form. This is axial methyl, first carbon atom. Here also axial methyl. They are running opposite, so can be represented as trans isomer. So 1A, 2A is one conformer, and by flipping process, axial methyl group is converted to equatorial bond methyl group, and this axial methyl also converted to equatorial methyl by flipping process. So this is another conformer, 1E, 2E. When you go for Gaussian interactions, when this CS3 group, axial CS3 group has two Gaussian interaction with the ring CS2 group that we have seen. Similarly, this methyl group, axial methyl group, also has two Gaussian interactions. Thus, there are four Gaussian interactions in AA form, whereas in EE form, there is no such a Gaussian interaction between the equatorial methyl group. We have seen when equatorial methyl group comes, there is no Gaussian interaction between the ring CS2 group and the ring CS2 group and the methyl group. But there is a Gaussian interaction between about 1,2 bond between the CS3 groups of this equatorial and this equatorial. Thus there is only one Gaussian interaction existing in EE form, whereas here four Gaussian interaction exist. Thus EE form is more stable than AA form. in trans isomer. Let us see the next position isomer, 1,3-dimethyl cyclohexane. 1,3-dimethyl cyclohexane has two geometrical isomers, cis and trans. This is a cis isomer where the CS3 groups are coming in same direction, and this is the trans isomer. CS3 groups are running in opposite direction. 1,3. Cis and trans. Cis and trans isomers are not interconverted to each other by flipping. This isomer has independent existence and trans isomer. This is a Fischer position formula drawn in eclipsed conformation. You have to go for staggered conformation. Actually, the molecule exists in staggered conformation. So we have to draw the chair form of cyclohexane, and when you look at when two CS3 group, in the position 1 we have CS3 group axial position, in position 3 we have axial position like this. So AA form represent the cis form because the CS3 groups are coming in the same direction. Due to flipping, the axial bond can transform to equatorial bond. This axial also converted to equatorial bond. One flipping, this one axial equatorial bond, this axial bond is transformed to equatorial bond, and here also equatorial bond. Let us analyze. This is 1A 3A and this is 1E 3E. Let us analyze the relative stability between these two conformers. When we have already discussed, when you have an axial methyl group, we have two Gaussian interaction between the ring CH2 groups. Here also there is an axial methyl group. Here also there are two Gaussian interactions. Thus there are four Gaussian interactions here. Whereas here the CS3 groups are in equatorial position. This CS3, equatorial CS3 has no Gaussian interaction with the ring CH2 groups. Similarly, this CS3 has no Gaussian interaction with the ring CH2 group. There is no Gaussian interaction exist in 1,3 conformer, and this will be more stable than axial cis isomer, cis conformer. This is also cis conformer because CS3 groups are running in same direction. So among cis isomer, this conformer is more stable. And let us look at trans conformer. In trans, this is a trans isomer of 1,3-dimethyl cyclohexane. For getting trans isomer, we have to go for chair form. This is axial CS3. One methyl group is placed at axial position. The other methyl group is placed at equatorial position. This methyl group is upward direction and this methyl group is downward direction. This conformer can be regarded as a trans isomer because one is upward, this methyl upward, and this methyl coming downward. This is a trans isomer. So we can say that 1A, first position 1A, and the third carbon atom we have equatorial conformer. When undergo flipping, axial methyl groups are converted to equatorial and equatorial methyl group are converted to axial. So one will become in this methyl group, equatorial methyl group, and this axial methyl group, equatorial methyl become axial by flipping process. So let us evaluate the relative stability. Here one methyl group is there. There are two Gaussian interaction between the ring CH2 group. For equatorial CS3, there won't be any Gaussian interaction. There is two Gaussian interaction here. Here also there is one axial methyl group. There will be two Gaussian. So these two conformers are equally stable. 1A 3E and 1E 3A are equally stable. Let us see the next isomer 1,4-dimethyl cyclohexane. 1,4-dimethyl cyclohexane is another position isomer of dimethyl substituted cyclohexane. Here one methyl group is at position 1 and another methyl group at position 4. There are two geometrical isomers possible, cis and trans. They can be separated. Here this is a cis isomer when CS3 groups are along same side. This is a cis isomer when CS3 groups are opposite side, running opposite. It is trans isomer. This is a Fischer projection formula in eclipsed conformation. Actually the molecule exists in staggered conformation. and for that you have to go for chair form. And this is when one methyl group is at the axial position, first position 1, this is in the upward direction. Here in the methyl group can be placed only at equatorial, because for cis isomer the methyl group should run in same direction. This is also upward direction, but axial isomer is actually downward, so we should not place like that. So this is actually axial methyl group, and this is equatorial methyl group. Whenever there is an axial methyl group, there are two gauge interactions. On flipping, the axial methyl converted to equatorial methyl, and the equatorial methyl is converted to axial methyl. So here this is 1A 4E and 1E 4A. And whenever there is an axial methyl group, there will be two gauge interactions. Equatorial methyl group will not have any gauge interactions. Here also one axial methyl group is there. There are two gauge interactions. So these two conformers, we have two gauge interactions. So these two conformers are equally stable. When you come to trans 1,4-dimethyl cyclohexane, which conformer is more stable? Let us evaluate. We can have first position 1 we have axial methyl group, position 4 we have axial. Then the two methyl groups are running opposite as shown in the Fischer diagram, and this conformer is a trans conformer 1A 4A. And during flipping, after flipping, the axial conformer is converted to equatorial conformer, and this axial also converted to equatorial. So this conformer is also possible 1E 4E. And this conform, let us evaluate the stability of difference between two conformers. Whenever there is an axial methyl group, there are two gauge interaction between the ring CH2 groups. We have already discussed. Here there is one axial here and another axial here. There are two gauge interaction in fourth position also. So that total there are four gauge interactions in 1A 4A. Whereas when equatorial methyl groups are coming, no gauge interaction taking place between ring here this CH3 group and the ring CH2 groups. Here also there is no gauge interaction. Here there is no gauge interaction in 1E 4E. Whereas here there are four gauge interactions. There is therefore 1E 4E equatorial conformers 1E 4E is more stable than axial. So in equilibrium mixture we have more amount of 1E 4E than the axial conformers.